functions, linear functions. So a linear function is one that takes the form of f of x is equal to ax plus b, or when we were doing coordinate geometry of the line, we would be more used to seeing that in the form of y equals mx plus c, where m was our slope and c was our y-intercept. But because this is functions, a lot of the times our lines are going to be given to us as g of x or h of x or f of x. The graph of a linear function, if we were to draw it, is going to be represented by a straight line. So if we look down here at the bottom, we have f of x is equal to 2x minus 1. And if we were to graph that between the domain of 0 and 2, then what I can do is I can make out a table where I have x, my input. I have my function, which is 2x minus 1. When I input 0 into my function, I'm going to have 2 times 0, which is 0, minus 1. Then my answer, 0 minus 1, is going to give me minus 1. So minus 1 is my output. And therefore, as a coordinate to sketch it, we would get out to 0 and up to 1. My end point in my domain here is 2. So if I put 2 into the equation 2x minus 1, I get 2 times 2 minus 1, which is 4 minus 1, which is, of course, 3. So my coordinate would be out to 2 and up to 3. So if I was to plot those points on my graph, I get out to 0 and down to minus 1. And I get out to 2 and up to 3. And of course, if I wanted to convince myself that it's definitely a line and that there isn't some random point over here making it a curve, like so, then you could always take a point between 0 and 2 there, such as 1, which would give me 2 times 1 minus 1, which is 1. So I'd be going out to 1 and up to 1. And now I can clearly see that there are 3 points, and if I join them, I am definitely getting a straight line. Okay? So, of course, you can be told in the question that it's a linear function. And if you weren't sure, well, then you always look at the power of x. So the highest power of x here is 1, which means it has to be a linear function. 2 other ones that are important to note here are this one. When we get x is equal to a, then we get a line through a, which is parallel to the y-axis. So parallel to the y-axis would be this red line down here in the bottom right-hand corner. And I can see it passes through minus 4. It's parallel to the y-axis. Therefore, this line would be x equals minus 4. If I look at the blue line, I can see the blue line is parallel to the x-axis, and it passes through the point 5. So therefore, this line would take the form of y equals 5. So what that means is that every point on this line has a y value of 5, no matter whether it's positive or negative for x. X equals minus 4 means that every x coordinate on that line is minus 4. Even though the y values are changing, the x value remains constant at minus 4. So with each of the functions that we're going to draw in this chapter, we're also going to look at what kind of transformations can take place with each of these functions. So if we look at a linear function, when we graph a function under a transformation, the graph will change its shape and its location, or its location. There are only 2 possible changes that can take place for linear, and that's that the slope can change, or that the y-intercept can change, or both can change. So if we look at these 2 examples of the graphs down here below, if my original function is f of x is equal to x, well, if I double the coefficient of x, I'm changing the slope, which means I now have a bigger angle made with respect to the x-axis. Whereas if I look at a half x, I can see I've decreased the slope, and therefore the gradient with respect to the x-axis is now smaller. So we'll see that the line is still passing through the same y-intercept, which is 0 there. So that hasn't changed. So there's only one change made to each of these lines, and that's the slope. Or you can even have x equals minus x, so we get this red dotted line here. If we look at the second change, if I change the y-intercept and keep the slope constant, I can see that each of these graphs have a slope of 1 because the coefficient of x in each case is 1. That we say the slope is constant in each of those lines. The only thing that's changing here is the plus c. So I have plus 2, I have plus 0, and I have minus 2. So that means I'm cutting the y-axis at 2, I'm cutting the y-axis at 0, or I'm cutting the y-axis at minus 2. But because the slope is constant, we can see that the 3 lines are parallel. So you're going to go to page 137 in your books. And you're going to do question 1. And then you're going to do question 13, 14, and 15. So for our quadratic functions then, they're always going to take the form of ax squared plus bx plus c. So in other words, the highest power of x is going to be a power of 2. We know that we can't ever have the coefficient a equal to 0 because then that would make the function linear. When we sketch our graphs, we're always going to get a parabola. So in other words, we're going to get a U shape if x squared has a positive coefficient, or an N shape if x squared has a negative coefficient. And again, like we did there with the linear function, we're going to complete our tables, but this time we're going to need more than 2 inputs to get the shape that we want. So if we look at an example of drawing our graphs, we have 2 functions here, f of x and g of x, and we're going to sketch them between the domain of minus 3 and 2. So we're going to start by making out our table. So if we make out our table for between the domain of minus 3 to 2, then we're going to have minus 3 squared plus 2 times minus 3 plus 2, which gives us 5. So we have out to minus 3 and up to 5. If I put in minus 2, we end up with the 2. If we put in for minus 1, this is 1. If I put in for 0, we end up with 2. If we put in for 1, we end up with 5. And if we put in for 2, we get 10. So if we draw our graph, well, we're going to need to do g of x and f of x on the same scale. So we may as well make our table for g of x out as well, so at least we know what's the highest and lowest y value we need, and what's the highest and, well, we know our x values are going to be between 2 and minus 3, but at least we can have a proper scale for our y-axis. Okay, so for g of x, we have minus x squared minus 2x plus 5. So it's going to be minus times minus 3 squared minus 2 times minus 3 plus 5. And if I do that all the way down, which gives us 2, so minus 3, 2, and 5, we get 6, and then we get 5, we get 2, minus 3. Okay, so drawing our graphs then. So always remember important to label our graphs. So our blue graph is f of x, so we can see it's a U-shaped graph, and our red graph is our g of x, and again we can see it's a negative coefficient for x squared, so we get an N-shaped graph. And we can also see that we have these 2 points where the two graphs meet or intersect. So if I mark those 2 points in green, and we could always read down from the x-axis to find out exactly what are their x values, and you could even read across to find out exactly what their y values were for the 2 points of intersection. So the question then asks us to use our graph to estimate where do the graphs meet. So for what x values is it equal? As I said, we can see there from the graph that it's minus 2.6 and also 0.6 approximately. So depending on how accurate your graph is, we'll all have slightly different answers, but should be almost the same. And the second part of the question then says, estimate the values for x for which is f of x is greater than or equal to g of x. So we have to write down the range of x values for where is the blue function above the red function. So where is blue above red? So I can see blue is above red when I'm going in, I'll mark it in green. So if I go beyond this point of intersection, then the blue graph is higher. So this portion here is above the red. And if I also go to the right then of 0.6, again we can also see that the blue graph is above the red. So we would say f of x is greater than g of x where x is less than or equal to minus 2.6, and also where x is greater than or equal to 0.6. And again, we have to use the equal to because we were given equal to. If we just said where is f of x greater than g of x, then we would just say x is less than minus 2.6 or x is greater than 0.6. Okay, so let's look at a question to draw. So again, you're going to go to page 138 in your book. And you're going to do question 5, question 8, and then you're going to do question 10 and question 12. So just in terms of types, if we go back to the start, we're saying for each of our functions that we're going to sketch, we're going to say type 1 is our linear. And we have A, which was drawing the graphs, and B, which was our transformations. Then we have type 2 is our quadratic functions. And again, A is where we're looking at drawing the graphs. And then B will be our transformations. So in our quadratic functions, what we're going to see is rather than linear only having 2 changes, the quadratic functions are actually going to have 4 changes that can take place. So the graph can basically move up or down the y-axis vertically. The graph can move horizontally, so left or right on the x-axis. The graph can be reflected in the x or the y-axis, and the graph can also be stretched up or down. So our first transformation would be moving it vertically up or down. So essentially what we're doing is we're changing the y-coordinates here. So when the graph moves vertically up the y-axis, then a number is added to the function. So in other words, we're changing the y value by adding this amount to the y-coordinate only. If we subtract a number from the function, then it will move vertically down by that number. So in other words, we would subtract the number from all of the y-coordinates. So say, for instance, if we look at this graph here, if we look at the blue one being f of x, let's say each of these boxes are 1, 2, minus 1, and minus 2. And each of the boxes going up are worth 1, 2, 3, 4, 5, and 6. Then if I was to pick one of my coordinates on the blue graph, let's say it was out to 2 and up to 1, 2, 3, 4, 5. And if I pick another coordinate off the blue graph, let's say it's out to 1 and up to 2. and out to 0 and up to 1, and out to -1 and up to 2, and out to -2 and up to 5. Okay, so let's say that's my graph f of x, whatever the function is. If I was to look at f of x plus 2, so in other words, I was moving my graph vertically upwards, then the y-coordinates are the only thing that's changing. So it would become 2, 7. 1, 2 would become 1, 4. 0, 1 would become 0, 3. -1, 2 would become -1, 4. And -2, 5 would become -2, 7. So we would see with that we would get each of these points have been transformed by literally just moving them up 2 places on the y. Okay? And we would do the same then if it was f of x minus 2. We could simply get our new set of y-coordinates. So we would take 2 from 5 this time, take 2 from 2, take 2, take 2, and take 2. Okay, and then you'd be able to do a sketch, rough sketch based on these new coordinates. So the x values staying the same, the y is the only thing that's changing. So the second transformation is when the graph moves horizontally left or horizontally to the right, parallel to the x-axis. And it moves horizontally left when we add a number to x. If we subtract a number from x, it moves to the right. So our y value will stay the same. The only thing that's changing is the x value. So again, we could look at our original graph. So let's look at the blue graph being our original graph. And we could write down a series of coordinates from that original graph. So let's say each box is 1. We'd be going out to 1 and down to -2. We could look at out to 2 and down to 3. I could take another point from the other side. Let's just stick with 3 points this time. Out to 0 and down to -3. So if that's my original function, if I'm told that it's f of x plus 2, then this means that I'm adding a value to my x, but the graph actually moves to the left. And that's if you think about it being a root. If our root is x plus a equals 0, then x equals minus a. So it's actually moving to the left. So that means I'm going to actually subtract 2 from the x coordinate. In order to shift it left. So that would become then -1, -2, because the y value is staying the same. So we have -1, -2 is this point here. We then have 0, -3, which is this point here. And then we would have -2, -3, which is this point here. So again, each of those points have been shifted left by 2 units. And then if it was f of x minus 2, so in other words, if the x has -2 taken away from it, we would actually move the graph to the right by adding 2 to each of the x coordinates. The third transformation we can have is if it's reflected in the x-axis or reflected in the y-axis. In other words, if the graph is flipped. So the graph is reflected in the x-axis when the function is multiplied by -1. So if you multiply the function by -1, essentially what you're doing is you're multiplying the y-coordinate by -1. If the graph is reflected in the y-axis, then the x value is multiplied by -1. So again, if we look at our graph here, we can see the first graph is reflected in the x-axis, and we can see that all of the x values are staying the same. So out to 2 is still the same, but we're going up to 1. So this coordinate here would be out to 2 and up to 1. If I multiply the y coordinate by -1, I can see that that becomes 2 minus 1. And we can do this with a series of different coordinates. So out to 4 and up to 5. Well, if I multiply the y coordinate by -1, I get out to 4 and down to -5. And again, you can do that for a series of points in order to get the shape of the graph correct. If it's reflected in the x-axis, in the y-axis, again, we would do the same. Pick a couple of points. Obviously, this point here is going to be itself, because if it's reflected in the y-axis, I'm multiplying the x value by -1, which is 0, so that's not going to change. So if I was to pick this point here, we have out to 1 and up to 3. And then if I multiply that by -1, well, the x is multiplied by -1, so that gives us out to -1 and up to 3. And of course, we could take this point here, which would be out to -4 and up to 3. And if I multiply the x coordinate by 1, well, I get out to 4 and up to 3. So again, we can do that for a series of points on the graph, and we would get the reflected points, and then we'd be able to sketch our graph. So the last transformation then is if the graph is stretched up or down by multiplying by a constant. So if a is greater than 1, in other words, if we're multiplying by a whole number, then what happens is the graph gets narrower as a increases. And that's because we're multiplying the y value by a. So the y coordinate is the only thing that you're changing. So again, you'd make out your xy coordinates for your original graph, and then you would take the y coordinates and multiply it by whatever the number is in front of the original function. If, however, the number is a fraction that we're multiplying by, then what's going to happen is the graph will actually get wider. So again, we can see here, if we have the original function as y equals x squared, and I look at that coordinate there, it's out to 3 and up to 10. Well, if I'm changing the y value by a third, I'd be getting 10 over 3, so it's just above there. So again, we can see each of our y coordinates will change as a result, but the x values are staying the same. So always making out your table. What's the original function? What are we changing? The x coordinate or the y coordinate? Adapt your new coordinates to get your new set of coordinates and then sketch your graph. Or you could always be given the graphs and then asked to identify what change has been made to it. In other words, what is the transformation? So let's go to our books, which is page 139. And you're going to do questions 16 to 19. So 16 and 17, you're given the graphs and you're asked to identify which function matches which based on has it been shifted up or down the y-axis, or has it been shifted left or right on the x-axis, or has it been reflected, or has it been narrower or wider? And then 18 and 19 asks you to sketch the original function and then hence as a result sketch the following functions. So for 18 and 19, make out your xy coordinate list and then adapt it into a new list of xy coordinates depending on what change you're making to the x or the y value.